Howdy. So in this video, we are looking at the strength of carboxylic acids. And um, in some ways, what's in this video is nothing new because we've talked about acid strength in terms of pKa's before, and we've talked about the different trends. But this should serve as a reminder, and it's easy to forget about acids and bases. I don't know how, because it is fundamental and so cool. So let's dig in here. So remember, carboxylic acids have this general formula: some group connected to a carbon that's double bonded to an oxygen with an OH attached. And so when it comes to carboxylic acids, kind of like we ended up the last video talking about, this hydrogen right here is acidic. And so it will get transferred to a base. In an acid-base reaction. And so depending on the strength of the carboxylic acid or the strength of the base, this equilibrium may favor entirely the product side. It may favor entirely the reactant side, or be somewhere in between. And so that's kind of what we're going to look at today: is how do you decide in a situation like this. And so we'll look at carboxylic acids and some of the effects on acidity. When we'll bring back the concepts of electron withdrawing groups, electron donating groups, and in terms of the inductive effect, what's the effect of having more of these groups nearby or fewer of them? How does that change the acidity? And just as a refresher, we measure acidity using pKa. And remember, don't confuse this with pH, which just is measuring the hydronium ion concentration in a solution. No, this is essentially an equilibrium constant that describes how easily an acid gives up its proton. And remember, pKa is the negative log of the Ka, and that's the equilibrium constant itself. So because of that negative sign, when something has a higher pKa, it is a weaker acid. And when something has a lower pKa, it is a stronger acid. Meaning that the stronger acid is far more okay with giving away its proton, its H+. Okay, and remember, we've got lots of different functional groups we've talked about, and they all kind of, we have this scale of pKa values, and so we're focusing on carboxylic acids here, which tend to have pKa values around 4. They're not as acidic as HI, HBr, HCl, and sulfuric acid, but still a lot stronger than something like water or alcohol. And so when we've talked about acids, and we've talked about structural factors that affect the strength. And remember, the stronger an acid, which means a smaller pKa, generally means that, well, always means that its conjugate base is weaker, right? That's the form that does not have, that has lost the proton. The conjugate base is what you make after the proton has been lost. And usually that, if an acid is stronger, it means that the conjugate base is more stable. So if I compare HCl going to its conjugate base, which is chloride, obviously plus H+. And I compare that, and that's an equilibrium. Or I compare that to acetylene going to its conjugate base. We all know that this first reaction essentially goes to completion in the presence of even water. And in fact, I probably shouldn't use these arrows like this. We know that HCl has a pKa of -7, whereas acetylide has a pKa of near, or acetylene has a pKa near 25. This is a huge difference. This is 10 to the 32nd difference in pKa. That's a really, really, really big number. So HCl is so much stronger of an acid, and part of the reason for that is when we look at what happens when the proton is lost. Well, here we have a chloride ion, and we know that chloride is large. It can handle that negative charge. It's also electronegative. Right, so it's able to, it's okay with having extra negative charge because it's an electronegative atom. So both those work together to make a rather stable conjugate base. Now, if we compare this to acetylide, well, carbon is smaller, certainly than chloride. Carbon is also less electronegative. Right? It's not as comfortable having that negative charge. So for acetylene to lose its proton is not a good thing, because its negative charge ends up on a small atom that's not electronegative, in contrast to chloride. That's why we see such a huge difference in the pKa values. And so these are all things we need to consider, these trends, when we're thinking about acid strength. Electronegativity and size, we just talked about those up there. These three, electronegativity, size, hybridization, relate to the atom attached to the hydrogen. Whereas the inductive effect and resonance, those are more global effects. So other features of the molecule. All right, so we will look at some examples of this and be able to apply these trends, just to give you a little review. So when it comes to resonance and acid stability, being able to delocalize the negative charge in the conjugate base stabilizes the conjugate base, right? So and just remember how this terminology works, right? If I call this HA, and let's say it's reacting with water, so it's dissociation in water. If this is the acid, it's going to give its proton to water, and we're going to make H3O plus, and the conjugate base of the acid. So this is the conjugate base. It's the acid minus a proton. Right? And so this is the proton that gets transferred in the reaction. This expression itself is the equilibrium expression for Ka, the acid dissociation constant. So if we're able to stabilize the conjugate base, we're going to lower the energy here. That shifts the equilibrium to the right, to a larger K sub A value, which means a smaller pKa. So we stabilize the conjugate base, equilibrium constant gets larger. Equilibrium shifts to the right. Which means that the pKa gets smaller, which we know corresponds to a stronger acid. Right, so this should be not come as a surprise. So if we compare three compounds, cyclohexanol, phenol, and benzoic acid, and we look at the pKa values for each of these, we see that going from cyclohexanol to phenol and benzoic acid, we see pKa is decreasing, which means increasing acid strength. So compared to cyclohexanol, benzoic acid really wants to give away its proton. So let's think about why that is. And nearly every time you want to answer this question of what is the strongest acid, you're going to look at the structure of the conjugate base. Is the conjugate base stabilized? And if we can do that, we're going to make a stronger acid. Okay, so let's draw the conjugate base. Cyclohexanol. Let me put this up here to indicate we're drawing conjugate bases of these species. So cyclohexanol loses a proton, which puts a negative charge on oxygen. Phenol also loses an H, loses the proton, put negative charge on oxygen. Benzoic acid also has negative charge on oxygen. So from that standpoint, they're all on oxygen. Oxygen is the same size, equal electronegativity. But let's think about these negative charges, and are they fixed on that atom or are they spread out? Well, if we look at this oxygen here, what's the carbon atom attached is sp3 hybridized, right? There's a hydrogen attached here. So that charge has nowhere to go. So this is a localized negative charge. It's not resonance stabilized. If we go to phenol, however, in this case we have a benzene ring, which means that the negative charge is not fixed on one site, and in fact we can draw a set of resonance structures showing that charge spread throughout the ring. So we have 4 resonance structures. The negative charge can go throughout the ring, the benzene ring, to go on different carbons. In the case of benzoic acid, it's not the aromatic ring, but instead negative charge can move up to the other oxygen. All right, so we have here, down here, 2 equivalent resonance structures. And they both have negative charge on oxygen. Which is a beautiful thing, because we know that that's going to be a very stabilized structure. Negative charge on a more electronegative atom. We love it. So here is, but if we compare that to phenol, yes, we have perhaps more resonance structures, but the other 3 forms only have the charge delocalized onto a carbon, which is not as attractive. And so that explains this difference in pKa values as we go from cyclohexanol to phenol to benzoic acid. We're becoming more and more acidic, increasing acidity. The reason for that is as we go in this direction, we are at the same time we're seeing increasing conjugate base stability. Okay, so let's think back to just our discussion of aromatic substituents. Because now what we're going to do is look at what is the effect of having other groups around on the acidity, acid strength of a carboxylic acid. We just explained why carboxylic acids are so much more acidic than phenols and certainly than a regular run-of-the-mill alcohol. And so to explain that, or to explain now what the effect of substituents are, if you recall, we talked about how we described substituents as electron donating groups, electron withdrawing groups, right? These groups that tend to be more electronegative are going to be electron withdrawing groups. They take away electron density. Electron donating groups donate electron density. And we saw that because electron donating groups tend to, when it came to benzene, they would activate the ring. They'd make it more electron rich. That's how you know something's donating electron density. So this chart kind of reminds us of some of those things. But now, one thing I want to point out, though, is the difference between inductive versus resonance donating ability. Right, remember something like an ether, for example. It donates through resonance because of the lone pairs. But it withdraws by the inductive effect, sort of through the bonds instead of through the pi system. So that is something to keep in mind as we go through this. Let's first look at inductively electron withdrawing groups. So when you have an electron withdrawing group nearby, they can stabilize the negative charge on the conjugate base of the carboxylic acid and increase its acidity. And so some inductively electron withdrawing groups are nitro groups, carbonyl groups, halogens. Alcohols and ethers. Those are on that list too because, as I just pointed out with the ether above, alcohols and ethers can pull, because they're electronegative, they pull electron density towards themselves. And if they can't donate through resonance, because there's not a conjugated system, they're useless as donating groups. So here is an example of a series of carboxylic acids. And the more electronegative the nearby substituents are, the more stabilized the conjugate base will be. So notice here we have on the left acetic acid, right? So these are all the carboxylic acid forms. And what we'll do down here is draw the conjugate, or at least a few of the conjugate bases. Right, and so as when acetic acid gives up its proton, it has this structure. And let's compare that to fluoroacetic acid. Right, and what's the difference here? Well, fluoroacetic acid with a pK of 2.6 is a much stronger acid than acetic acid. In fact, as we go left to right, we're seeing stronger acids. And the same thing that's happening is the electronegative pull of the substituents is also increasing. A nitro group is very electronegative. Fluorine is more electronegative than chlorine. So as we go in this direction, we're seeing more electronegative substituent. And the other thing that happens is because of the more electronegative substituents, we have as we go in this left to right, we have more stable conjugate bases. And why is that? Well, that is because this fluorosubstituent, or any of the electronegative substituents, pulls electron density towards itself, right? And that pull gets transferred kind of throughout the whole molecule. And so that the negative charge that's on between those two oxygens in the carboxylic acid conjugate base is spread a little bit through the molecule. So it doesn't seem quite as big and bad and scary. Whereas with acetic acid, we know that the CH bond, it's not really polar at all, but if it was, electrons would actually be going in the other way, kind of towards the carbon. So this inductive pulling of electron density in fluoroacetic acid on the right here stabilizes the conjugate base, stabilizes the negative charge. And so the more electronegative that substituent is, the more stable the conjugate base will be. But there's also an effect of having more electron withdrawing groups, right? So as I start to add more chlorosubstituents, look what happens to the pKa of the acid. Go from 4.8 to 2.8 to 1.3 to 0.9. So it's an additive effect. The more groups I put on there that are pulling electron density, the more they're going to stabilize the conjugate base. So as we go left to right, increasing acidity. And there's also a proximity effect. So if the electron withdrawing group is closer to the carboxylic acid, as in the case of the structure on the left here, where that chloro group's on the second carbon, we're going to see a stronger acid, right? So it has a stronger pull. Its effect is stronger when it's nearby. So like, for example, here, this chlorine is pulling electron density, but there's all these groups in between, and so they sort of insulate the carboxylic acid from the chloride. Whereas in the case of the structure on the right, the 2-chloro butanoic acid, they're very close, and that chloro group has a very large effect on the stabilizing conjugate base. So those are kind of the three classic effects, and those effects really play a role in any type of acid-base process, whether it's an alcohol functional group or carboxylic acid. So let's talk for a second here about inductively electron donating groups. So electron donating groups destabilize negative charge in the conjugate base and decrease acidity. So the main example of inductively electron donating groups are alkyl groups. So here's an example where we have acetic acid, and then we have propanoic acid, where there's a methyl group. And here's on the right is pivalic acid. And in this case now, we're seeing increasing acidity in the opposite direction. And so to think about this, let's look at the conjugate bases. There we go. Well, remember that alkyl groups are effectively electron donating. And so we are actually pushing electron density by being a donating group. Those methyl groups are pushing electron density towards something that already has a negative charge. So that's a destabilizing effect. If you've got negative charge, if you're sitting there with negative charge, you're going to say, hey, hold on, I don't want any more electron density. I've got enough. So that's the effect of alkyl groups, is they're pushing electron density or any kind of donating group towards something that already has it. And so so that's a destabilizing effect. So as we go, we see increasing acidity right to left now, and which corresponds to increasing conjugate base stability. Okay, so how about for benzoic acid, and what's the effect when resonance is involved? So here's the structure of benzoic acid. It has a pKa of 4.2. These are all pKa values. And notice as I go in this direction, I have electron donating groups. They're pushing electron density towards the carboxylic acid, which is going to destabilize it. So these make this a weaker acid. But now as I go in this direction from benzoic acid, notice I'm having electron withdrawing groups. We have a chlorosubstituent. We have a nitrosubstituent. These are electronegative. We have another nitrosubstituent. And so these make the carboxylic acid a stronger acid. Now there are probably two questions you might be asking. First of all, didn't we just refer to the methoxy group as an electron withdrawing group just a little bit ago? And the fact is we did. But here's a case now where resonance is involved because of the ring. So let's look at the conjugate base of benzoic acid with the methoxy group. So we'll investigate this a bit more here. Remember that methoxy group has lone pairs. And now that we have a pi system, this can actually be donated through resonance. And in fact, we can put a negative charge this actually puts a negative charge next to something that already has a negative charge. So this effect is destabilizing, or it's unfavorable. And so this molecule is worse off, this conjugate base is worse off than it would be if there was no methoxy group and it was just benzoic acid. So that's why methoxy group, because it can donate through resonance, actually leads to a weaker carboxylic acid. Now, if we compare this to the nitro groups, and in particular, let's look at this nitro group right here. Now we must be somehow stabilizing the conjugate base very well. So here's the conjugate base. Right, so how would this work? And let me actually draw out the nitro group here. Well, we know that the nitro group can accept electron density, and which means it can draw electrons from the ring. And so it puts positive charge character into the ring. And then we can move that to here, and throughout the ring. And so by putting positive charge into the ring, it stabilizes the ring. So this nitro group stabilizes the conjugate base through resonance. And the inductive effect. All right, so both those things are favoring withdrawal of electron density from the ring. All right, so here is an interesting example for you to think about. Why we talked a little bit about the methoxy group and how it, in the para position, it acts as a withdrawing group or a donating group. Since it increases the pKa, makes it less acidic. And here, it lowers the pKa and acts as a withdrawing group. So why this difference? And so on the previous slide, we drew this resonance structure for the conjugate base of the paramethoxy benzoic acid. Oops, let me draw that. And we noted that it was pushing electron density towards this thing that already had electron density. We said that's unfavorable. In the case of the meta-methoxy group, we end up with this conjugate base. And now remember that this methoxy group can withdraw through the inductive effect and can pull electron density from the ring. And it can also donate into the ring. And can put electron density here. Electron density can move to here. And here. But the point is, it moves everywhere in that ring except for that carbon, right? So it's not putting electron density directly on the carbon attached to the carboxylic acid. So that's why it has a net destabilizing or a net stabilizing or withdrawing effect, because it does not electron density directly to the carbon attached to the carboxylate. In the benzene ring. So it has a net stabilizing or net withdrawing effect. So that's part of why we see this difference in how the substitution pattern can affect the product. Okay, so the last thing think about are a few applications of what we know. And so you at this point, you should be able to predict the products of an acid-base reaction like shown and indicate whether the reaction favors products or reactants. And you really shouldn't need a pKa table for this because you have learned the principles of acids and bases. And so you should be able to see that, of course, this right here is the acid. This is thing with the negative charge here is going to act as a base. And so the product is going to be this compound. Right, so we have our acid and the base. This is the conjugate base. This is the conjugate acid. Right, so the question is which is favored, which side is favored. So let's see. We could do two things. We could compare the conjugate bases, and between a negative charge with a CH3 group attached, or a negative charge with a CF3 group attached. Well, we're going to go with the CF3. That's going to really stabilize the charge. So between these two, this base is more stable, right? Which would suggest that that side of the equilibrium is going to be favored. We could do same thing, compare the two acids. We got CF3, CH3. We know having electronegative groups attached makes something a stronger acid. And so we know this would have a lower pKa. It is more readily gives up the proton. So the equilibrium is going to favor the products, because the more stable base is on that side and the weaker acid. All right, and then lastly, if we look at pentanoic acid, also known as valeric acid, it's fairly insoluble in water. Now, it's actually I looked it up after I made these slides. It's actually 5 grams per 100 milliliters, I think at 25 degrees Celsius. So it's not that insoluble, but it's not miscible with water. And so this is pentanoic acid, 5 carbons, or valeric acid. And so the question is, how do we make this dissolve? And so right now this is neutral, but if we were to add a base to it, now we've gone from something that is neutral to something that is ionic. And so this is going to be much more water soluble. Because we have removed that proton, we've made it charged. Water loves charged molecules, so it loves to dissolve them. So that's kind of the key, and you've used tricks like this in the lab where you've done acid-base extractions. A lot of times you did a wash with a base to remove excess acid. Well, this is pretty much what you're doing. You're turning the acids into their conjugate bases to make sure they dissolve in water and get removed from the organic layer. I'm sure, kind of as a last example, you've all heard of, I'm sure if you've looked at labels, you've seen something like potassium benzoate or sodium benzoate. I'm going to draw it up here. So for example, sodium benzoate. It's a preservative, and it's the sodium benzoate. It's the conjugate base form. It's like that so that it's readily soluble in water or whatever you're using. It's often drinks that it's added to. And so If you ever wondered why, that's one of the reasons, is to make sure it's readily dissolved.